Welcome back to Multigrid Methods. So we're talking about um, this concept of the cell-centered finite difference method in Chapter 7. And what we're going to show is that this chapter is deeply connected to the information and the theory that we just developed in Section 5.9. And so the reason is because, as we're going to see shortly, the method that we create here doesn't satisfy the standard Galerkin condition. It satisfies this scaled, what I'm calling now the imbalanced Galerkin condition. And we have to do some different things in order to analyze how the convergence happens. So that's what we get when we kind of mess with things. Sometimes things work out and sometimes they don't. And by don't work out, that means we have to do a lot more work to get the convergence that we want. Last time we were talking about the difference between these three sets of functions. So the functions were VL, and then there was another function space that we called CL0, and there was another function space called CL interior. And I said all of these functions can be related to each other. And by the way, they can all be related in the end to R and L. Okay, so they're all isometrically isomorphic to this very simple space, and or at least isometric, or yeah, isometric. I think isomorphism means that you also have some kind of norm equivalence as well. In any case, so they're all related to this space, this very simple Euclidean space RNL. Now, what is VL? VL is the space of piecewise constant functions. So for example, it would be a function which looks like this. Piecewise constant, and they're constant over these intervals, which we're calling the cells. Okay, so there are 4 cells in this example. Piecewise constant on those individual 4 cells. They only have values at these 4 points. This function space, CL0, is a set of cell-centered grid points which has homogeneous Dirichlet boundary conditions. That's what the comma 0 means. So that's a function which looks like this: 1, 2, 3, 4 interior points, but it also has these values at these ghost cells. So remember, the ghost cells are to the left of 0 and to the right of 1. So this point here, by the way, is precisely equal to, that's x equals 0, even though it's not written there. And this point here is exactly x equals 1 in our terminology. Now, that's what a function from that space looks like. It has interior values, but it also has values of these ghost cells. And the values of the ghost cells are chosen exactly so that the average of these 2 points, if I were to take the average to be defined at this point, is exactly 0. So if I think about that as being a line, okay, a linear function between those, connecting them, then clearly the average of those 2 values is 0 at that point. And the same way with this point here, its average is equal to 0 at this point, x equals 1. The way you do this is very simple. You just set, well, I'm going to say VL5 is going to be equal to minus VL4, and VL0 is equal to minus VL1. Okay, so that's how I can establish functions from that space. What about functions from this space? CL superscript circ. This means interior. So that function is defined only at these 4 interior nodes. Okay, so 1, 2, 3, 4. It doesn't have degrees of freedom out here and here, but we could easily create those degrees of freedom by saying, well, okay, I can identify a function from here with a function from here just by saying I'm going to set those values to be minus the values of this point and this point. And likewise, if I start with a function here, I can easily reinterpret it as a function from this space because these aren't really degrees of freedom out here. They're linked to these values here. So they're not independent degrees of freedom. So each one of these spaces has dimension 4 in this example, and in general has dimension NL. And that's why they're intimately linked. And I can think about a function, a cell-centered function, as being from any one of these function spaces. And they really are function spaces, because if I add two functions together within any of these spaces, I get another function back in the function space. So these can be linked together in a canonical way, and they're really the same description of, they're really different descriptions of the same fundamental thing. All right, so, I wanted to go back and talk about this. So this is, in symbols, exactly what I just said by a picture. So there's a one-to-one correspondence between vectors in R and L and the functions of VL. And this correspondence is denoted as usual like this. So this means function from the piecewise constant space of functions, and it's connected through this basis BL. Remember what the basis BL was? Basis BL was the set of piecewise constant functions that were basically characteristic functions on each one of the individual grid cells. So for example, one of the piecewise constant functions might be like this. Okay, it's 0, and then it's equal to 1, and then it's equal to 0 again. Okay, so I have 4 of those individual basis functions, and those 4 individual basis functions comprise this basis called BL. Now, anytime I have a V expressible in a basis, then I can peel away the coordinates of that expression in the basis, and I can call that its coordinate vector from the basis. And that's exactly what's done here. If I do an expansion of VL in the basis, BL, basis elements from BL, those are piecewise constant functions that are 1 on certain cells and 0 everywhere else. Then, of course, I'm going to get these coordinates, and I can bring those coordinates together and put them into a coordinate vector VL. So that tells me how to do this correspondence between VL and RNL. Now, likewise, there's a one-to-one correspondence between vectors in R and L and grid functions in this grid function space CL0. And that's because if I look at this, this really isn't a separate degree of freedom. Okay, so I can take either one of these guys to be the degree of freedom. The one I do, the most natural one, is to say the value here is going to be an independent degree of freedom, not this one. Okay, and so I can build a basis of that with that idea in mind and say, what should my basis be? Well, my basis is just going to be grid functions that are basically delta functions. So they're 1 at certain cell-centered points and there's zeros everywhere else. Well, if that gives me a basis, then again, I have this coordinate vector representation owing to that basis. I'm going to call that basis of Kronecker delta functions GL. I can peel away the coordinate representation, or the coefficients in this basis representation, and I can call those the coordinates of my VL vector. Okay, so this is how I make these identifications. In one sense, I'm making the identification between this space and this space, but I can also make this identification directly. I don't have to pass through this this space. I can say, I know how to make a function that for example, if I have a function that's a cell-centered function with homogeneous Dirichlet boundary conditions, I can connect it or immediately come up with the related or associated function from this piecewise constant space and vice versa. Okay? And I think the picture tells the whole story there. Now let's talk about a finite difference approximation for the Poisson problem, problem 1. So let me go back and show you what that Poisson problem looked like. It's our regular standard Poisson problem minus u double prime equals f in the domain 0 to 1, excluding the boundaries, and u equals 0 at the boundary points, the 2 boundary points. So what I want to do is approximate that by a finite difference method. How can I do that? Well, what I'm going to do is I'm going to look for, let's see. Yeah, here's the slide I want to land on. I want to look for a grid function from CL. Remember, CL means grid functions that actually contain the ghost cells or have values at the go cells which are independent degrees of freedom. And I'm gonna eliminate those as degrees of freedom through the choice of what I call boundary conditions in just a second. All right, so I want to look for a grid function which is defined at every grid point, including the ghost cells. And I'm going to set the average of U to be equal to 0 at essentially x equals 0. And I'm going to also set the average to be equal to 0 at essentially x equals 1. And then in the middle of the grid, okay, in the centers of the grid or the interior of the grid, I'm going to use my standard 3-point finite difference stencil, or the 3-point finite difference approximation, minus UL I minus 1 to UL I minus UL I plus 1, all divided by mesh spacing, which in this case is just 1 over NL, the mesh spacing squared, and that's going to be set equal to the value, to the known value of F at the grid point XLI. So that's how I define FLI. It's the function F evaluated at XLI. All right, so what does this look like? So let's say I take a function and I want to evaluate this operator on it. So I'm going to make a grid, and this grid maybe only has 4 cells. Okay, so that means it has 4 interior cell-centered grid points, and it also has 2 ghost cells, one which is to the left of 0 and one which is to the right of x equals 1. So let's label that. X equals 0, x equals 1. Now, I want to choose a function which is going to satisfy these 2 boundary conditions. What should that look like? Well, just like what we said before, the things at the edges, the values of the functions at the edges should have the average being equal to 0 at x equals 0. So for example, if the value of the function is this negative value at the first grid point, right? So that first grid point is going to be xl1, and this is xl2, xl3, xl4. And of course, this is going to be xl5 and this is going to be xl0. Well, if that's its value at that first grid point, I'm simply going to take the value at the go cell to be the negative value of that. And similarly, if it has that value at that cell center grid point, I'm going to take its negative at the go cell. And then otherwise, it might be some function which looks like this. Okay, so its functions are here, 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 and here, function values. So that could be a function that comes from this space and satisfies these 2 boundary conditions. Then I'm going to apply the usual 3-point finite difference stencil at all the other interior values. So I from 1 to NL. In this case, NL is equal to 4, so I'm going to apply the 3-point stencil here, 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 and here. So what's required to apply the 3-point stencil? Well, I need the value that comes before this one, so that's that value. So I need this value. I need that value, which is that value there. And then finally, I need this value, which is found here. Okay, then I combine them together and I get a value. Hopefully that value, once I divide by HL squared, ends up being FLI, right? And same here, I can apply now the stencil here, and that requires these 3 points. I can apply the stencil here, which requires these 3 points. And finally, I can apply the stencil here, which requires 1, 2, 3 points. And then, of course, I said I've already applied these 2 conditions to ensure that the average at x equals 0 and x equals 1 is exactly equal to 0. So this is different than the vertex-centered finite difference scheme that you've seen before, because in the vertex-centered finite difference scheme, we simply had values at the boundaries and we set immediately those values to be equal to 0. We eliminated them from degrees of freedom. But for the cell-centered finite difference case, we don't have that luxury. We don't have a an exact value at the boundary points x equals 0 and x equals 1. And so we have to determine the values of our approximation via this averaging technique. That's the notion or the essence of the cell-centered finite difference method. So this is one way of doing it. An equivalent way of doing it is just say, well, hey, let's just require our grid function to come from that space of homogeneous Dirichlet boundary conditions, or cell-centered grid functions with homogeneous Dirichlet boundary conditions, so that CL0 function space. Well, if I do that, then these two boundary conditions are taken care of automatically. I don't have to do anything extra. All I really have to do is enforce my 3-point stencil at all the interior grid points, which is those grid points with index between 1 and NL. The boundary conditions are built into the space of solutions, a lot like they are when we deal with the finite element method. The boundary conditions are built into the space of solutions. So in the cell-centered finite difference methodology, we're going to obtain this approximation. What do we mean by an approximation? Well, that should be approximately equal to the true solution evaluated at the cell-centered grid points. Now, it's not exactly equal to the values there. It's only approximately equal. And remember, we know that the mantra that we talked about in numerical analysis was the following. The true solution satisfies the boundary value problem. The approximate solution satisfies the equations of the finite difference method. And they don't satisfy the same set of equations, right? This will satisfy the finite difference method up to what's called the local truncation error, etc. They're not the same function. However, if I measure the difference in some norm, for example, this norm here, this works out to be some norm. I think in numerical analysis, we wrote it like this. We said UH minus U, and we called this the L2 star norm or something like that, L2H norm. Okay, so that's how you get that. But in any case, this is some sort of norm. And the difference, the norm of the difference between those two objects is less than some constant times HL squared. That's what you can show. And in fact, we're not going to do that in the book specifically, but you can go to our book from the Big Purple Monster from 2023, and you can see how this is going to be done. Okay, so remember, the finite difference method is only an approximate, gets you an approximate solution of the true solution, the PDE solution. Well, now we have NL equations in NL unknowns from either this or this. This actually has NL plus 2 equations in NL plus 2 unknowns, but we can immediately eliminate this as a degree of freedom in a simple and easy way, and this one as well. So we can turn it into something which looks like this. And so you can write out pretty quickly NL equations in NL unknowns by eliminating those two, the values of those two ghost cells. And what you get then is a set of NL equations and NL unknowns that can be turned into a matrix vector equation. So we can gather up the vector of unknowns that we want to solve for. We can call that the U vector, UL vector. And then we, of course, have a set of known values from the forcing function f, and we're going to gather those into a vector we're going to call FL, right? And then we're going to use our equations to construct what's called a stiffness matrix. And the stiffness matrix in this case is a little bit different than the stiffness matrix that we've encountered in previous chapters. It looks a lot like the standard stiffness matrix, especially the standard stiffness matrix for the finite element case, or for the finite difference case, that we developed in chapter 3, except for it has this weird 3 here and here. So this equation, or this matrix is no longer, it no longer has a constant diagonal entries. Previously, the diagonal entries were all 2 in chapter 3. Now, the diagonal entries differ in the first and the last position. Instead of 2s there, they're going to be 3s. And the reason why this happens is precisely because of that weird accommodation of those boundary conditions involving those ghost cells. All right, so this is what we're going to call the cell-centered stiffness matrix. It's a little bit different than the matrix that we've met before, again, because of this entry and this entry. So you can imagine its properties may be a little bit different. One question that should immediately come to your mind is this matrix invertible? Is the matrix symmetric? Is it positive definite? So right away we can see, of course, that it's symmetric, but the question is it going to be positive definite? All right. So let's give this, as I said, let's give it an official name. That's going to be called the level L stiffness matrix. Okay. And there we are. There we have it. Level L stiffness matrix. So pretty. Now you've heard me say it before. There's this thing in math land called Gilstrang's favorite matrix. Gilstrang's favorite matrix is the matrix which it's the standard stiffness matrix. It has 2s on the diagonals, whereas this one is slightly different. It has a 3 on the at the first and last diagonal entries and 2 elsewhere. So I'll call this Steve Wise's favorite matrix instead of Gilstrang's favorite matrix. But they're related. They're close cousins. In fact, we can show that this stiffness matrix is still SPD. In fact, its eigenvalues and eigenvectors are eerily similar to the eigenvalues and eigenvectors of the standard stiffness matrix, Gilstrang's matrix. For example, or in particular, its eigenvalues are NL in number exactly. And remember, the difference between this case and the standard finite difference finite element case is NL here is always going to be even. And previously, NL was always odd, okay? In the finite, well, mostly always, at least in the multigrid context, we were always taking NL to be odd. Well, that's only for chapter 3 sort of stuff. Now in chapter 7, we're going to assume that NL is usually always even. They're exactly NL eigenvalues in number, and they have exactly the same functional form as previously, except the big difference here is how HL is defined. Previously, how did we define HL in the context of the finite difference, the standard finite difference method? So for the standard finite difference method, we always decided to have HL to be NL plus 1, if you remember. So NL was odd, but NL plus 1 was even, typically. All right, so now we're going to do this differently because in the cell-centered context, HL is always chosen as 1 over NL. The 1 comes from the fact that we're on the unit interval, 0 to 1. So that's one big change. And then I'll discuss another big change whenever we plot these things out. But otherwise, the functional form is the same previously. It's a sine squared, it's a cosine, okay? It's sine squared k pi HL over 2 times some prefactor for k between 1 and NL, okay? The corresponding eigenvectors are, again, similar to what we found for the standard stiffness matrix. They're sine modes, okay? The big difference here is how the sine modes are defined. For example, here we're using cell-centered points. We're not using vertex-centered points. Okay, so these sine waves have slightly different points of definition. Okay, so there's still, now, whether you want to think about them as grid functions or think about them as vectors, it doesn't really matter. It's okay to think about them in both ways in the current context. So how do we prove this? How do we establish that these are the eigenvalues and these are the eigenvectors? Well, if somebody tells you that they're giving you some eigenvectors then you can always test that claim by just plugging in the eigenvectors that they're claiming are eigenvectors and seeing if you get the right values out. So if somebody gives you an eigenvector and says, I think this is an eigenvector of AL, so you grab it and you say, well, let's see if you're right. You plug it, well, you multiply it by AL, and then you should get out an eigenvalue, lambda LK, in return times that vector VLK. All right, so there shouldn't be any confusion here. If somebody tells you here are eigenvectors, do the matrix vector multiplication and see if you really do get eigenvector or the eigenvalue times an eigenvector in return. So we'll see that that's exactly what we get in this case. Now let me check something interesting here. These do not have values. If I view them as grid functions, they don't have values at the so-called ghost points. They don't have values at xl0 and xl_nl plus 1. However, I can check to see that the sine function, if I just follow the pattern of putting in these values and assuming that this obeys the formula for cell-centered points, I can show that sine k pi xl0 equals minus sine k pi xl1. So in other words, this sine function satisfies the homogeneous Dirichlet boundary conditions if I consider it as a grid function. All right. So that's the first thing we want to put into our pocket. What else do we know? Well, we know that AL is clearly symmetric. So all we need to show is that it's positive definite by showing that all of the eigenvalues are positive if these truly are eigenvectors and eigenvalues. So let's do the computation. The easiest way to do the computation is let's take HL squared times the stiffness times the quantity of the stiffness matrix times the proposed eigenvector and evaluate that vector at the location or at the component I. So if I do this computation and I look at it at component I, what I get is pretty interesting. Minus sine k pi xl I minus 1. Remember, this guy here is a cell-centered point. Plus 2 times sine k pi xli. That's a cell-centered point. Minus sine k pi xli plus 1. Now I just realize, okay, xli, okay, let's look at actually xli plus 1. That's exactly equal to xli plus hl. What this means is if I look at one grid point to the left of where or to the right of where I am, it's equal to that grid point that I'm at plus HL. Okay, so this says that the neighboring grid point to XLI is just differing from it by a value of HL. What if I look at the grid point this was the grid point here to the left. Now or to the right, let's look at the grid point to the left. That's going to be Li minus 1. That's the grid point at XLI minus HL. Now I'm just going to use a sine and cosine formula, trigonometric formula, sine addition formula, I think it is, to show that I can actually combine these three terms into one big term, all of which has a common factor of sine k pi xli, using again that standard trigonometric identity. However, it's going to be multiplied by 2 times 1 minus cosine k pi hl. The 2 comes from the fact that I can just remove this guy right away, and that's 2 times sine k pi xl. And I turn these guys using the sine angle summation formula. One of the terms cancel, and the other term has a cosine in it, or cosine k pi hl times sine k pi xli. Now we notice that this prefactor here is completely independent of I. That's good. And also I notice that because of my little relation here and here, I can run this computation without change for every grid point, even equal to I equals 1 and I equals the NL. So right up next to the boundaries. This computation that I do is invariant. And so I show that what you get back is essentially the values of the eigen, the values of the components of the eigenvector, that's that guy, times some constant which is completely independent of I. And of course, that guy there is just the eigenvalues, right? Now, I don't have this HL squared. Where does that come from? It comes from the fact that I multiplied this guy to make the computations a little bit simpler by HL squared. So if I want now, I can bring this guy down and put it in the denominator. And so I have 2 over HL, and that's exactly this formula that I have here. Now I can use another trigonometric identity to convert this guy into sine squared, this function, times 2. And but I'll leave that to you guys to do. All right, so now I have these as my eigenvalues. Now a quick plot shows us that all of these eigenvalues are positive, and I'll show you a plot of that in a moment. So if I can show that all of these guys are strictly positive, then I've got it. All my eigenvalues are positive. I have a symmetric matrix, so I have a symmetric positive definite matrix. So here's what the eigenvalues look like. If I plot them for the case NL equals 8, there are going to be exactly 8 eigenvalues. 1, 2, 3, 4, 5, 6, 7, 8. And of course, they satisfy this formula. You can either write this as a sine squared function or 1 minus a cosine function. They differ only by a factor of 2, right? So either I could plot it like that or that. And they're exactly the same functions, and I get exactly 8 eigenvalues. And I can see right away that these eigenvalues are between the values 4 over HL squared on top, and they go as low as almost hitting 0, but not quite 0, right? So they get close to 0, but this guy is definitely not 0. It's definitely positive, so all the eigenvalues are positive. Now, one thing that's different about this whole scenario between the previous finite difference method called the vertex finite difference method, or the standard finite difference method, is that this last eigenvalue is always exactly hits this roof, hits this ceiling up here. Whereas in the standard finite difference case, the last eigenvalue was always this guy. So it started to get asymptotically close to 4 over HL squared, or if I have the analogy of that, where this is the last eigenvalue or the largest eigenvalue, then it's going to get closer and closer and closer to 4 over HL squared as HL gets smaller and smaller, or NL gets larger and larger, however you want to look at it. Here, the last eigenvalue actually hits this upper limit exactly. So that didn't happen in the standard finite difference case. It does happen in the cell-centered finite difference case. But it doesn't matter too much to us. It's just a distinctive characteristic. The main point is that the smallest eigenvalue is always positive. Okay, so that gives us our positive definiteness. I'm going to skip over that. So just briefly, this just says that my last eigenvalue actually hits this upper limit. And that differs from the finite difference case where the last eigenvalue did not hit the upper limit. And I have a typo here that I want to flag. So typo, broken reference. Okay. We'll skip that point otherwise. Now, what about the eigenvectors? So the eigenvectors, you may remember this famous theorem, which says if you have a symmetric matrix, then you have an orthonormal basis of eigenvalues, or eigenvectors, sorry. If I have a symmetric matrix, then I can always have an orthonormal basis of eigenvectors. So that is true if you properly normalize them. And these sign functions, these sign modes, are not properly normalized to give us an orthonormal basis. However, we still do have an orthogonality relationship. Okay, so if I take so they're orthogonal to each other, meaning that if I take vectors, let's say VLK1, and I dot it with VLK2, where K1 and K2 are not equal to each other, then this dot product is going to be 0 for K1 not equal to K2. Now, if K1 and K2 are equal, then what we can say is that the value of that dot product, or the inner product, okay, however you want to call it, standard Euclidean inner product, this is basically a dot product, they're always equal to these constants beta Lk, which are not one uniform number. They depend on K. So for K equals NL, it's just NL. But for K less than NL, then less than or equal to NL minus 1 specifically, the normalization constant is NL over 2 when I take the dot product of these two vectors together. Okay, so this is now if I want to go back and make them all orthonormal, I could go back to my definition of the sine functions and divide them by these values so that I get the proper normalization. In fact, you have to divide by the square roots of these functions so that when I take them pairwise, I'm just going to get ones. So this is a headache and a hassle. We don't want to worry about that. So we're just going to keep these, we're going to keep them unnormalized so that we can keep these sine functions in place. So now this is an interesting feature. If you looked at the same calculation done for the standard stiffness matrix in the finite difference case, then the normalization factor was always exactly the same. Okay, I forget what it was. It was either maybe NL or NL over 2, but there was no dependence on K. And so now, because we have a different stiffness matrix, our normalization changes slightly. All right, so now we know all of the eigenvalues, and so we know that the ratio of the largest eigenvalue to the smallest eigenvalue is going to give us what's called the condition number of the stiffness matrix. And as we showed in chapter 3, we can always prove that this condition number is bounded above by some constant times HL to the minus 2 power, and bounded below by another constant, positive number, positive constant, HL, positive constant times HL to the minus 2 power. I guess it would be less of a mouthful if I would write these things like this. This is C2 over HL squared, and this guy is C1 over HL squared. So this says that the condition number is basically asymptotic to HL to the minus 2 power. And we usually use some sort of asymptotic symbol. So the one we chose to use is something called big theta. This is a common one as L goes to infinity. And all this means is precisely this. Roughly speaking, it says the condition number is just some constant times HL to the minus 2 power. That's it. Okay, so this tells us that we have a fairly ill-conditioned stiffness matrix. As HL gets smaller and smaller, which is what you want with a more and more accurate computation, the condition number deteriorates. It gets larger and larger. Okay, and so this bodes ill for our standard general linear iterative schemes like the Jacobi method, or like the Gauss-Seidel method, or even something called the SOR method. So if you look in chapter 1, we discussed this. If the condition number starts to get very large, then usually the convergence rate of the general linear iterative scheme deteriorates kind of badly. It doesn't behave well. And so that's exactly what's going on here. If I were to throw a standard general linear iterative scheme, one of those naive little schemes that we derived in chapter 1 at a problem like this, it's not going to work very well, especially for HL being small. All right, the next topic I want to talk about is a smoother. We know that that's an important or integral part of a multigrid or two-grid algorithm. What are you going to do about smoothing these? What are you going to do about smoothing so that you can get the error to be smooth on the high or on a fine grid and then push it down to a coarse grid to do some work on it. And where the high frequency or for the low frequency stuff becomes high frequency on the coarse grid. We need a smoother to do that. It's an integral or an important part of multigrid methods, and the ones we've talked about so far are the damp Jacobi method and Richardson smoother. We also talked a little bit about Gauss-Seidel smoothers, and we're going to talk a bit more about that when we get into later chapters. There's only a couple more chapters, by the way, to go. Right. So currently it's called chapters 9 and 10, but we're in the process of adding a new, by the way, a new chapter 2. So those are going to get pushed a little further back. We're not going to go back and do the new chapter 2, turns out, but we are going to talk about these more, I would call them more abstract framework for doing multigrid in these later chapters. Okay, so damp Jacobi, Richardson smoother, Gauss-Seidel, what can we say about those in the context of cell-centered methods? Well, we're not going to say much, if anything at all, about the Gauss-Seidel smoothers, but let's say a little bit about damp Jacobi and the Richardson smoother. So after discretization of our PDE or I guess our boundary value problem in this case, we get this matrix problem on every level that we want to consider, right? Of course, whenever we do an approximation, we're thinking about applying these at some finest level, capital L. But otherwise, we have this family of linear systems that we could consider at every level in between 0 and L inclusive. So let's think about approximating the solution of 11 at some level L using one of our favorite GLIS methods. In particular, let's talk about the damp Jacobi method. So this requires taking AL and splitting it into a diagonal part, an upper triangular part, and a lower triangular part. In particular, we're going to take minus the lower triangular part and minus the upper triangular and minus the lower triangular parts separately. All right, so the diagonal part, that's pretty easy to see. We harped on that quite a lot, or at least I did. It's different than in the standard finite difference case because we have these weird 3s at the first and last entries, and otherwise we have 2s. The problem with this method becomes apparent right away, and that is this diagonal matrix is not a constant diagonal matrix. So that's going to give us a little bit of problem or some problems. What about minus the upper triangular matrix? Well, for our stiffness matrix minus the upper triangular matrix, oh, I have a typo here. What is the typo? So for AL, right, it's 1 over HL squared times these things. So I need to put in here 1 over HL squared and 1 over HL squared. Okay, missing that. But otherwise, they're constants, right? So the upper triangular part is 1 over HL squared times zeros everywhere except ones on the super diagonal. And of course, the lower triangular part is just the transpose of the upper triangular part. So the damp Jacobi, how do we formulate that as a smoother or an iterative method? Well, the way you do it is you throw U and L over to the other side, and then you divide by that diagonal matrix DL. And so when you not divide by it, but you multiply by its inverse, etc. And so you get this initial approximation value that we call ZL sigma plus 1. And then what we do in the weighted or damp Jacobi method is we weight it with a parameter omega, where omega is some number between 0 and 1. Not 0, because if we use 0, then basically that is just using the old value of u, and it doesn't give us any new approximation. And if I take 1, then that's just the standard Jacobi method entirely. Now we can eliminate ZL sigma plus 1 and just write things in a standard way. Okay, and this is a very simple thing we talked about from chapter 1, and this tells us immediately what is our iterator matrix, right? So this is the matrix we called B previously, or B inverse. I forget what we called it. But in any case, so that's our iterator matrix here. And in the context of multigrid, we give that iterator matrix a special term, right? It's called the SL matrix. And in this case, it's going to be omega times DL inverse. The associated error transfer matrix is, of course, I minus B times A in general, or IL minus SLAL in this multigrid context. And so then I just put in that matrix there and I get that. So that's my error transfer matrix. Now, what makes all of the analysis simple for the standard finite difference case and for the finite element case is the fact that for this damp Jacobi method, this diagonal matrix is just constant entries. And so that means that effectively this thing out front that appears is just one big fat constant. That's no longer the case here because this D matrix is not a constant diagonal matrix. These threes throw things off. All right, so that's the difficulty for our analysis with the damp Jacobi method. The diagonal entries break this nice property. So that means effectively that my K matrix, my error transfer matrix for the smoother, does not have the same eigenvalues as the stiffness matrix, right? If this was just a constant, then this whole thing would be a constant. And it's fairly clear right away to see that the error transfer matrix for that method, damp Jacobi smoother, has eigenvectors, sorry, which are exactly the same as the eigenvectors for the stiffness matrix. This is very important because this makes our analysis a lot easier. So we're going to stick with the easy way of analysis, and we're going to reject this method because it doesn't have that nice property that we want. So what should we use as a smoother? Well, it's Richardson's method to the rescue, because Richardson's method always has that nice property that you have the eigenvectors of the error transfer matrix are the same as that for the stiffness matrix. And that's because by definition, Richardson's method always is expressed like this. The error or the iterator matrix is always just a constant. Okay, so in that case, it's fairly easy to show that for the error transfer matrix, which I'll exhibit in a moment, that we have precisely the same eigenvectors. Now, what we do with Richardson smoother is we talked about this a while ago, and Richardson smoother in this case means we're going to take this kappa value, this free parameter, to be a certain particular value. In particular, we take it to be the reciprocal of the spectral radius, or the largest eigenvalue. Now, in this case, we have a nice firm formula for our largest eigenvalues. Our largest eigenvalue is just going to be 4 over HL squared. Okay, so this is a little bit different than the case that we had for the finite element, and for the standard finite difference case. We couldn't say exactly. We couldn't give this largest eigenvalue such a nice formula in those cases. Here we can give it a nice formula. This choice where we replace this with lambda, the reciprocal of minus lambda L, or K the reciprocal of kappa is equal to lambda L. That means we're going to be dividing by 1 over lambda L here. Sorry, 1 over lambda L. I keep screwing that up. 1 over lambda L. Now lambda L is that, and so basically we're multiplying by HL squared over 4. That's what we call the lambda Richardson smoother. Now I want to give that a precise name, because what I'm going to do is I'm going to use a scaling. I'm going to replace this kappa with another number, and I'm not always going to choose my kappa to be this way. That's what you do when you choose the specific lambda Richardson smoother. But I want to keep things open, and I want to analyze how does the smoother work if I change this parameter slightly. But I want to keep the scaling in a sort of similar way to the scaling I've had before. So what I'm going to do is I'm going to take the Richardson smoother and I'm going to replace the kappa that was there, and I'm going to replace it with another free parameter, omega, where omega is positive, but I'm going to multiply it by HL squared over 2. And the reason I'm going to do this is basically this matches the same form that we had in chapter 3. This is going to provide eigenvalues for our error transfer matrix, which are going to be roughly on the same scaling. And that way, the graphs that I produce are going to have the same scaling, etc. So now this is going to be what I'm going to call my general Richardson smoother or generic Richardson smoother, because it's still some constant times this residual here. So now if I take the I minus the iterator times A, then that gives me the so-called error transfer matrix. I'm going to call that kappa, and it's going to be a function of omega, because here omega is still a free parameter. I can choose whatever I want for omega. It's still generic. So this is my error transfer matrix for the general Richardson smoother. Now, if I take omega equals to a half, then this right away becomes HL squared over 4. Okay, if I replace omega with a half, HL squared over 4, that's precisely what I get when I use the lambda Richardson smoother. So lambda Richardson smoother is exactly this generic Richardson smoother when I take omega equal to a half. They're different in general, but if I take omega equal to a half, I get the lambda Richardson smoother. The reason why I chose this is because if you look back in chapters 3 and 4, then the lambda Richardson smoother in that case was also obtained by taking omega equals to a half. So that's why I did it. What are the eigenpairs of the generic Richardson's method? Okay, so because we set this up to be nice in a way, we already said that if you look at the error transfer matrix for the generic Richardson smoother, which I just exhibited here, I said it's clear, it should be clear that the eigenvectors are exactly the same as the eigenvectors for A, right? If I multiply this matrix times an eigenvector of A, then I'm going to clearly get a number times that eigenvector back. So that says that the eigenvectors of KL are exactly the same as the stiffness matrix AL in this cell-centered context. And we already showed what those eigenvectors are. They're sign modes. The eigenvalues of KL, this is pretty easy. Again, it's always easy to check. If somebody tells you that they have eigenvectors for a certain matrix, you can just stick it into that matrix and check to see that you get a number times the vector back, and you can confirm whether or not these are eigenvectors. And that's exactly what you do here. I'm going to leave it as an exercise for you to show that if I plug in these guys' potential eigenvectors, then I'm going to get, and of course I'm talking about for KL, I'm just going to get a constant times those eigenvectors back, and the constants are what I'm going to understand as my eigenvalues of KL. And in this case, it's this seemingly complicated formula, but again, I've taken the scaling for the choice of my constants to be exactly so that the plots match up to be more or less the same as the ones that we had in chapter 3. So if you remember back in chapter 3, we had a plot which looked like this. And if I pick omega equals to a half, that gives me the lambda Richardson smoother. So this guy is lambda Richardson. Lambda Richardson. This is the most important from our context. So this is the one we're going to use. And what it says is that, remember, we had this concept going all the way back to chapter 3 of high frequency modes and low frequency modes. Now, what smoothers do is they damp out high frequency modes of the error really well, but they don't damp out the low frequency modes of the error so well. So what the lambda Richardson's does is this value here is a half. I didn't write it on here, but this value here is a half. And if I take omega equal to a half, then it says that for all the high frequency range are wave numbers k, which are between NL over 2 and NL. So it's this range here. That's the high frequency range, and this is the low frequency range for this particular grid. Well, this says that it's going to damp high frequency modes by at least a factor of a half in the high frequency range. And actually, as you get higher and higher frequency, it's going to dampen those modes faster and faster because that damping is almost zero. Now, if I choose to take omega equal 2/3, then I have kind of an even better smoothing property. I can say that all of the high frequency modes are made less by a factor of a third. Okay, so here's plus a third and here's minus a third. So if I want all of them to be damped by a factor of a third in absolute value sense, then if I take omega equals 2/3, I get my damping factors, which is precisely what these eigenvalues measure to be between plus and minus a third. Now, if I don't do anything with the generic Richardson smoother, by that I mean I set omega equals to 1, then I get I get very poor damping because here there's no damping at all. This is exactly equal to 1, so there's no damping action happening. The only damping I'm getting is near the midpoint of the high frequency, low frequency range. Now, all of these curves, no matter what values of omega I choose, all have for the very lowest frequency terms, all of them basically do no damping at all for the lowest frequency modes. And that's what's exhibited here. There's no damping action at all. Here, I'm having good damping for these two choices, okay, for all the whole range of the high frequency range. But here, I have no damping at all. If I choose omega equal to 1, then here I have very little damping either. So basically, that's saying that if I use this lambda Richardson's, which is kind of like saying I use the Jacobi method without any damping at all, then basically it's not a good smoother. So this is a good way of analyzing how good of a smoother you have. If you follow the multigrid's prescription, then you want to choose a smoother that has the smoothing characteristic. It really damps the high frequency components of the errors out really well. Okay, I'll skip that. So the spectral radius of the generic Richardson's method. The spectral radius of the error transfer matrix tells us how good the method converges as a standalone method, a general linear iterative smoother. Well, you can see right away that the spectral radius for the generic Richardson is going to be it's going to be around 1, right? It's going to be roughly this eigenvalue here. Okay, so now I have to be a little bit careful because this last eigenvalue down here when I choose omega equals to 1 is exactly equal to minus 1. So that's bad. So I'm really focused on this range down here. What are, remember, the first eigenvalue appears somewhere right in here. So that eigenvalue is very, very close to 1. In fact, what we can show is that if we take that first eigenvalue, we can take that guy and we can multiply it by 1, I guess. Let's see. Not multiply it by 1, add or subtract 1 from it. Basically, it's roughly equal to 1 plus a number, which is big theta of HL squared. So this guy is basically going to 1 very, very fast. So if the spectral radius is going to 1, that's basically saying that your method as a standalone solver is basically useless. And it gets worse as HL gets smaller and smaller. This is also explaining to us why the condition number plays a role, because this is like the reciprocal of the condition number. As the condition number gets worse and worse, then the spectral radius of the general linear iterative scheme gets worse and worse as standalone smoother. And so basically it's saying the standalone smoother or this as a standalone solver, these general linear iterative methods are basically crap. They're basically useless and they shouldn't be used. That's what this result is saying. Now I'm going to skip the proof of that because the proof is really the same as what was in chapter 3. The details are slightly different because, well, why are the details different? The details are slightly different because remember the eigenvalues are a little bit different. They're not exactly the same as in chapter that we dealt with in chapter 3. Okay, but for the lambda Richardson smoother, it has this property that whenever I put in, well, to get the lambda Richardson smoother, we put omega equals a half in. And the lambda Richardson smoother, just by looking at the plot of those eigenvalues, has the nice property that in the high frequency range, which is k between NL over 2 and NL, we have the eigenvalues associated to those frequencies, k, or those wave numbers, all being less than a half in absolute value. In fact, in total value, they're in their true values, they're less than a half. So here's a picture of it. Now I didn't plot on here. I did later on go in the book and put in the exact locations of the eigenvalues. They're discrete. They're not continuous, and they look something like that. All right, so it's clear that in this high frequency range, right, for the k values being in this range, all of them are bounded above by a half and bounded below by 0. And in fact, the damping on this highest frequency is really, really good. It's basically just, you basically have 0 error for the highest frequency terms. For the next highest frequency terms, you get the usual sort of damping. It's really rapid, but it's not quite 0. And going all the way up here to the let's say the lowest wave number in the high frequency range, it's damping that mode by at least a half. Okay, so that's the standard. That's one of the standard properties of the Richardson smoother that we wanted to inherit. So we're going to use this as our smoother for this method. Okay, so now if we use the Richardson smoother as our smoother, the lambda Richardson method, then we should be able, in the context of the multigrid theory, be able to show a smoothing property for this. So remember, multigrid methods basically are, we need some kind of Galerkin condition, we need some kind of approximation property, and we need some kind of smoothing property. So those are the big three for multigrid. We need some kind of Galerkin condition, or sometime understanding of how the Galerkin condition gets broken, at least. We need a smoothing property and we need an approximation property. So those are the big three we need to establish. So the first we're going to work on is the first smoothing property. We're going to show that our lambda Richardson smoother satisfies this. Now, it turns out, actually, there's not much to do here because the analysis that we did way back in chapter 4 is basically unchanged here. So if you want a reference for this, go back to chapter 4 and have a look, see how it was done there. And basically, it's going to be quite similar. So the one-dimensional cell-centered finite difference stiffness matrix is, of course, SPD. We can therefore orthogonally diagonalize it, or we can say AL is orthogonally diagonalizable. We can write AL as VL, DL, VL transpose, where VL is an orthogonal matrix each of whose columns is orthonormal, or I can say the columns form an orthonormal basis. So how do these relate to those sine waves that we developed earlier? Well, you can just use those sine modes for these columns, but you have to normalize them so that the resulting matrix VL is an orthogonal matrix. So for that to happen, the columns have to be not just orthogonal, but orthonormal. Now, if we orthogonalize AL by VL, then the diagonals are just going to be the eigenvalues, the positive eigenvalues of the matrix AL. Now, since these eigenvalues are positive, that's going to tell us right away that the stiffness matrix is SPD, but it allows us to do something kind of cool. And that is, for this SPD matrix, and in fact, any SPD matrix, we can define its square root. So the square root of an SPD matrix is just, if I refer back to that orthogonal diagonalization, is just going to be the same diagonalization, except I take that middle diagonal matrix dl, which previously contained the eigenvalues. And I'm just going to replace those with the square roots of those eigenvalues. And the reason I can do square roots is because, well, each one of those diagonal entries is a positive number. So taking the square root um, is doable in the classical sense. It's doable in the complex setting, all that you want, but in the classical real setting, these make sense. They're just now going to be positive numbers. And you can see right away that if I multiply this matrix times itself, keeping in mind that these V matrices are orthogonal, I'm going to right away get, so let's do it. So if we do AL 1/2 times AL 1/2, that's just going to be VL DL 1/2 VL transpose VL DL 1/2 and VL transpose. So these two annihilate each other because they're orthogonal matrices, and orthogonal matrices have the property that VL transpose VL is identity. Now, when I multiply DL 1/2 times DL 1/2, these two matrices here, I just get DL. And so it's pretty clear that what I get back then is just going to be DL, VL, DL, VL transpose. So that's AL. Cool. So that says right away that this makes sense as a square root. I have AL 1/2 power, AL 1/2 power is equal to AL. Okay, square matrix, and same size matrix. Cool. So that tells us that we can rewrite this standard energy norm for any vector in a different way, okay, a kind of useful way. So let's see how this is done. Remember, what is this by definition? This is the energy norm or the AL norm. So it's the square root of the AL inner product of VL against itself, which is, I can liberate this guy by replacing that with a Euclidean norm and multiplying either the right or left by AL. So I just choose to put it on the left-hand side. And now I'm going to break this AL into AL to the 1/2 power times AL to the 1/2 power. Each one of these ALs to the 1/2 power is itself a symmetric positive definite matrix. So I can take one of them and throw it over here, right? But now I quickly see that that's just the Euclidean norm of this vector AL to the 1/2 power times VL. So I have another way of writing what this object is in terms of the AL to the 1/2 norm. Now, in a similar way, I can define this object called the AL squared norm. Now, this is like a Sobolev H1 norm, and this is like a Sobolev H2 norm, as I reminded you guys about when we were in chapter 6. And this is going to be very important to us from the context, or in the context of smoothing, as I'll show you in a moment. But how do I reinterpret this as a different norm? Well, let's use the definition. So if I use the AL norm as the energy norm, that means it's a Euclidean norm, but with an AL squared written in the first piece. But I can break AL squared norm into AL times AL. And each AL is symmetric positive definite, so I can take one of them to one side and leave the other one over there. And then clearly this is equal to the standard Euclidean norm of the matrix times the vector, matrix AL times the vector VL. Okay, so that's just two ways of viewing these norms that are kind of commonplace a little bit differently. Now, we did mention this way back in chapter 4, but the same thing holds here in chapter 7 because we have this family of symmetric positive definite stiffness matrices lying around called AL. All right, now we need to establish the first smoothing property for our cell-centered finite difference method. And the way we're going to do this is we're going to assume that we're using Lambda-Richardson's method. And let me see. I may not have time to go through all of the details of this, but if not, then we'll come back and finish up these details next time. But at least I'll get the statement and a little bit of the proof out of the way. So let's assume that smoothing is carried out by the Lambda-Richardson smoother. So this is our standard smoother in this section where we take omega equal to 1/2. then there's some constant C0 such that for any M1 in the natural numbers and any WL vector, KL M1, so this is the error transfer matrix for Richardson smoother raised to the M1 power times WL, and we're going to measure that in this Sobolev 2 norm, AL squared energy norm. So this has a this kind of has the weight of a Sobolev 2 norm. This is less than or equal to a constant times the spectral radius of the stiffness matrix, lambda L over M1, times the AL norm of WL. And this is like the Sobolev H1 norm. Okay, so it has a similar sort of weight in the functional, or I should say, in the finite element setting, at least that's exactly what that means. Doesn't have quite the same meaning here in the cell-centered context, but in the finite element context, that's what these things mean. And I can even pin down what the value of this constant is. I can know that it's exactly equal to 1 over the square root of 2. So this says, if you go back and look at property S1, how that's defined in chapter 4, this precisely says that the lambda Richardson smoother satisfies property S1. Okay, how do we prove this? So the way we're going to prove it is just by pretending we know what we're doing and writing down the thing that we want to bound on the left-hand side, writing it out in all the details and see what we get. So if I write out what this thing is in all of its details, we argued that can be converted to a Euclidean norm by writing AL times the vector in question here. Okay, I'm going to square both sides, so that's why the square appears. Now, if I square norm, then and the norm comes from an inner product, then that just becomes the inner product of the vector with itself. Okay, so that's that vector repeated. Now, we know we have a basis of eigenvectors, correct, for the stiffness matrix AL, and those are the same eigenvectors for the K matrix. And in fact, they're the same eigenvectors for KL raised to any power, no problem. So we're going to write WL in that basis of eigenvectors for AL, using the eigenvector basis of AL. So these are the eigenvectors that we're going to use. Those are the sine waves. Now we don't have to use the normalized vectors that are in these columns here. That's just for theoretical purposes. They're not normalized, so I put these tildes on them. So they're not necessarily the same things, but we don't have to use those guys. We can use the unnormalized ones that we normally have around, the sine waves. Now, we're going to use the identity, the normalization identity that says that if I take the dot product of any two of those vectors with the same wave number, I should say the same eigenvectors with the same wave number, I get these constants called beta LK. And they depend on both L and K in this case. They're not just one value, because in this case, if K is equal to NL, I get a normalization constant of NL. That's what the inner product of these two things are. And if I have NL or K less than NL, between 1 and NL minus 1 in particular, then I get NL over 2. Now, it doesn't really matter what the normalizations are. When you do this expansion, most of the terms, so I'm going to throw this guy in here and also in here, although I'm going to use different expansion parameters. So I'll use, maybe let's say I'll use K in one of these guys, and I'll use another index, maybe J in over here. And remember, because of orthonormality, a lot of them are going to be 0. How do I know that? Well, first I have to multiply those vectors, right? So I have to take, let's say I have to take AL, KL, M, and I have to multiply it times WL. What do I get? Well, I'm going to get sum K equals 1 to NL, right? And so I'm going to get WLK, but each one of these guys here is an eigenvector of both these things, right? So I'm going to get mu, I think I called it mu LK, and that has to be raised to the M1 power. And then I also have the eigenvalues from this matrix, the stiffness matrix. What do we call those? We called those lambda L K. And this is not a power here. This is an index. And you can see that because I'm using the parentheses here. So I can put that in here and here using, of course, different summation indices, then using the orthonormality, or not the orthonormality, but just the orthogonality. And when I do that, I get these normalization constants. I'm going to get a bunch of eigenvalues that are popping out as well. Right? So I'm going to get eigenvalues from the stiffness matrix, and I get squared because I have them appearing on both sides. I get a square of these coefficients here because those appear on both sides. And then I'm going to get the eigenvalues for the for the error transfer matrix raised to the 2m1 power, and that's because I get m1 from this side and m1 from that side. Okay, so that's where that's the calculation that I've done there. Well, I have to stop there because we're out of time, but you can see we're almost to the end of the proof. Just have a few more details to go. But we can do that next time. There's no great rush there. And I will see you guys on Tuesday.